Thank you, and I would like to thank the organizers for the invitation to this nice conference, so Hertling, Sabah, and Semenek. Today I'm going to talk about joint work with Masaki Kashiwara on the Riemann-Hilbert correspondence. There are two papers published in 2016, one at IHES and the other at CREL. The one at CREL is only available electronically for the moment. Okay, so as you can see, there is an impressive blackboard estate. So I'm going to use the blackboards. Okay. So, yeah, that's the most difficult part of the talk. Okay, so the setting is the following. Let X be a complex analytic manifold. And consider Y, which is a hypersurface. So the classical regular Riemann-Hilbert correspondence was stated in the following form by Deligny in the 70s. You take a regular flat meromorphic connections with poles along Y. You consider solutions, or if you prefer, horizontal sections, and what you find are local systems on the complement. And when I say local system here, I mean finite dimensional and over C. So this was upgraded in the 80s, early 80s, by Kashiwara on one side and Mebkut on the other side, independently, to an equivalence between regular holonomic D-modules. On X. Now, Y does not play any role here. And again, by taking solutions, you find an equivalence with the category of perverse sheaves. And if you don't know what are perverse sheaves, you should think that there is a suitable stratification, analytic stratification of your space, along the strata of which you have a complex of constructible sheaves, and they are actually locally constant. The cohomologies are locally constant along the strata. But so that's an improvement on local system, and a big advantage of this point of view is that it is well behaved with respect to functoriality. So if you take a morphism of complex manifolds, then there are at the level of D modules the usual operations of push forward and pull back. I just write down the notations to fix them. I don't explain what they are, but if you have a D module on X, you can push it forward to Y. You can pull it back from Y to X, and you can take the tensor product of two D modules. Maybe tensor and pullback are also familiar in this setting. This operation is in a sense new because in general, if you push forward a connection, you no longer have a connection, but you still have a D module. And then there is a duality functor, and this equivalence of categories is compatible with the natural operations on the other side. Again, just to fix the notations, let me just consider the proper direct image, then the usual inverse image, the tensor product, and Verdier duality. Okay, so Kashiwara, in fact, was also able to construct a way to go back. So if you give me a perverse sheaves using Kashiwara functor, I can produce a regular holonomic D module. And then maybe in the early 90s, Deligny and Malgrange asked themselves what happens if you remove the hypothesis of regularity, and they did it in dimension 1, complex dimension 1. So in this case, what you get is what we know since we had a few courses by Sub and Ertling. You get what is called a Stokes filter local system. But then if you go in higher dimension, things get a little bit more complicated. And thanks to recent works by, 2011 by Mochizuki and Kedlaya, based on previous results and conjectures by Saba, you can also do something in higher dimension, but you need to add some assumptions. You need to treat what's called a good flat meromorphic connection. Then maybe you need to ask that the hypersurface is a normal crossing divisor. Anyway, by considering suitable filtration on the solutions, you still get an equivalence upstairs. And so what I propose to explain now is what happens downstairs here. So my joint work with Kashiwara, you simply suppress the hypothesis of regularity, and what you need to do is to enhance the category. These are just words, they don't mean anything, but I will try to explain. And so you should enhance everything, in particular you should enhance solutions. Then these functors get changed a little bit. I just write the correct notations, then I will say a few words later. You put an E in front of everything, and I put a plus here. Okay, so these are just notations, and that's what I would like to try to explain if the time allows. Okay, but as you see, I'm setting the bar very high, very, very high. And I start down to the ground in dimension 1 to briefly recall what you already know, thanks to what we heard before, but I really start with an open neighborhood of the origin in C, and I take Z, which is a complex coordinate. Since I'm dealing with the modules instead than connections, I prefer to speak about operators. So let P be a linear differential operator with holomorphic coefficients. I denote it by partial the holomorphic derivative. M is going to be the order. And that's a typical element, actually, of what's the sheaf of differential operators on X in general. In general, instead of having only one variable, you will have many, but it looks the same. So the idea is that apart from being an element of the base ring, you can also consider the associated cyclic module, which is the module that you obtain by quotienting the ring by the ideal, left ideal generated by P. D is non-commutative. And sorry? Yes, yeah, it was my joke, now I can. Okay. So what are the solutions in the module setting? Solutions are just the set of D-linear morphisms. So in particular, solutions of this D module are D-linear morphisms from the module into holomorphic functions. And actually, it's better to consider the full derived complex, which in this case is easy to describe. It's just the complex consisting of P that acts on O. So this is a complex of the derived category of sheaves of C-vector spaces on X. And you see that it encodes solutions in the sense that it has possibly two non-vanishing cohomology degrees. I put degree 0 here, so H0 represents the kernel, and H1 represents the co-kernel of your differential operator. Let me concentrate on the H0, so on the solutions, and let me assume that I'm interested in a neighborhood of 0, which is supposed to be an irregular point. Irregular means that the top degree coefficient vanishes, and of course let me assume that it does not vanish identically. So up to shrinking X, you can assume that's the only 0 of the top degree coefficient. So what I want to try to understand are the solutions of the homogeneous equation P of U equal to 0 in a neighborhood of the origin. Okay, so what we know, thanks to classical results by Fukuhara, Levet, and Turittin is that at least formally you can find a basis of solutions. So at the formal level, you can find some solutions that I put a hat to denote the fact that they are only formal. And so they have a special kind. They can be written in the form e to the phi I of some root of 1 over d of the coordinate. Then there are some monodromies, z to d lambda I, and then there are some formal series. So of, again, z1 over d. So here, d is an integer greater or equal than 1, then lambda I are complex numbers, and the phi i's are meromorphic functions with poles at the origin, modulo holomorphic functions, and you can actually choose pick up a representative in this case using the coordinate. So they are polynomials in z minus 1, beginning with z something times z minus 1. Okay, so these are called exponential factors. So as I said, here I goes from y to m, and this ui hat span a basis of formal solutions. But then you can improve it and get real holomorphic solutions. The price you have to pay is that you need to choose a direction. So if this is z equal to 0, you pick up a direction theta. And the statement is that for any direction that you choose, you can find a small enough open sector D where you can find real holomorphic solutions on this sector that I denote by ui without a hat, which satisfy the property of being asymptotic to the formal ones in your sector. And what does it mean? It means that if you consider the difference between ui and ui hat, of course, it is meaningless because this is only a formal series. So you need first to cut it. This is just a formal power series. You cut it at degree n, and I denote by uin what you obtain. So that's meaningful now. So if you consider the difference between these two for each n, this is estimated by some constant times e to the phi I, which is the corresponding exponential factor, times z lambda I plus n over d. And so you see, this is a component of moderate growth, and what counts most is this exponential part, which in fact contributes through its real part. I mean, the exponent, what counts is the real part of the exponent. Okay, this is what Fukuhara, Levet, and Turittin tell us. Of course, UI is not uniquely determined by this condition, because if you pick up, for example, if it happens that the real part of phi j is strictly smaller than the real part of phi I on your sectorial neighborhood, then the contribution of phi j is negligible with respect to phi I, and so indeed you can check that the uj solution, if you take ui and you modify it by any constant time uj, this is still asymptotic to the same. And now, thanks to this result, there are two ways of encoding enough information to be able to reconstruct the module associated to P, and these are respectively Stokes multipliers and filtered Stokes local systems. I briefly recall what they are. So first, Stokes multipliers. Stokes multipliers are based essentially on this kind of remark. So what happens is that now you pick up two directions, theta and theta prime. For each one, you choose a sector, d and d prime. They overlap. Let's assume that they overlap. So for the choice of d, you were able to find the basis of solutions holomorphic in d that I denoted by ui. You can do the same on d prime. So you can find a new basis, u prime I, which is asymptotic to ui hat, but on this new sector. And now if you look at the intersection, what happens is that you can, of course, write one basis in terms of the other. ui prime will be equal to the sum of a, I, j, u, j. And these are called Stokes multipliers. So that's the first way of encoding things. You need to cover punctured neighborhood of the origin with overlapping sectors, and you collect the matrices that you see. These are Stokes multipliers. The second way of encoding the information is by Stokes filtered local systems. And in this case, what you do is you take a real blow-up of the origin. So let me just draw a picture. Down, you have your point. Up, you take the real blow-up, so the point gets exchanged with a circle. And so, for example, if you take a direction theta downstairs, sorry, I pull up. If you take a direction theta downstairs, it corresponds to a point in the circle. And if you take a small sectorial neighborhood, as we are doing, it corresponds to a real neighborhood of the point in the blow-up. So inside the blow-up sits a circle, and this circle is in fact the circle of directions emanating from the origin. I will denote it by S0x. It sits inside. Then if you remove the origin, what you get is you can recover it both downstairs and upstairs. So let me denote by J, the open embedding, when I remove the point, J tilde, again, the open embedding, but when I send it in the blow-up, and I, the embedding of the circle. Okay? So what you can do is you consider usual holomorphic solutions of your D module, MP, and then you restrict it, you remove the origin, so you do j minus 1, then you push it forward to with the j tilde, you push it forward to the real blow-up, and then you restrict it to the circle. If you call it L, this is a local system on the circle. And then you can filter it in the following way. So if you pick up any function of that kind, not necessarily, of course, an exponential factor. So let now phi be your preferred meromorphic function. And at least at the level of Stokes, it's easy to say what is the filtered component of L at levels smaller. I think notations are a little bit different from Earthling, but I use these notations. So this is going to be a constructible subsheaf of L. It's going to sit inside. But let me first just describe what's a Stokes at theta. This is the set of solutions, homogeneous solutions in a sectorial neighborhood of theta that grow moderately with respect to, okay, let me write. So the absolute value of u should be smaller or equal than some constant times absolute value of z to some constant again times the exponential of let me write it like this, the exponential of the real part of phi. And, okay? So apart from the exponential, the growth should be moderate. If you move theta around, this builds up an R-constructible subsheaf of L. And the claim is that the collection of such data, again, is enough to reconstruct your D module. So you have these two different possibilities. But I want to discuss a third possibility, which I like more, and it's closer to what we are doing. So just 1 second. And I'm going to use the picture that Stokes himself drew in 1857, and Philip Bolch already used it. I'm going to use the Airy equation as an example to describe what happens. I'm sorry, it takes time. Maybe then I will ask a few more minutes. I'm joking. Okay, on the right is a piece of Stokes paper from 1857. He's interested in the Airy equation that I wrote up there. Its solutions are called Airy functions, AI and BI. You can look Wikipedia. Stokes computed everything in his paper, and in particular, you know that that equation has two entire solutions, so holomorphic everywhere. But there is an irregular singularity at infinity. So, as I said, you can consider the asymptotic developments. Of course, things are, I was speaking about 0, here is infinity, but okay. So we know that this is the kind of formal solutions that you find at infinity. So the exponential factors in this case are plus or minus 2z 3/2. So the d is 2 in this case. There is a unification. This corresponds to what are called regular components, but I don't care about them. This happens in a sector, and that's the sector centered around the real axis. So as I said, you should think of it as a neighborhood of infinity, and it works. It's very slow to react. Actually, it doesn't react. I'm sorry. So this is supposed to be green, so I lost time for nothing. I drew the sector there. But if there's a shade of green there, I'm sorry, I didn't test it on the wall. Anyway, it's not important. So what are the lines that Stokes drew? Actually, around here, he explains perfectly well what you have to do to draw these lines. You need to take into account the growth. So you need to take into account the real part of this phi. So what you need to do is to draw in polar coordinates in some way what the phi plus minus do. And so you pick up a strictly increasing function. Stokes chooses a linear function, and then you take a constant big enough so that absolute value z equal to c is a neighborhood of infinity. You restrict there, so you only consider points in the circle of radius r. And if you draw it by computer, you see that it fits in the blue one is by computer. So now let me get rid of the Stokes paper. This is what he says. And so now what I would like to do is the following. So we are in a sector that unfortunately is invisible, but believe me, there is a green sector here that is this one. Okay. Nevertheless, so let us say that when you write things like this, you need to pick up a determination of the logarithm in order for the square root to make sense. So you can do it in a neighborhood of the positive real axis. You do it. So now these are perfectly well-defined functions on the sector. And let us say that phi minus corresponds to the small a, what he calls the subdominant contribution in this sector. So let me draw the, I hope it, it's almost invisible. There's a light gray region here. I spent all the night doing, okay.
We see it once you say what it is.
Okay, so let us dream together. So I drew some light gray region there, which is what stay outside with respect to the subdominant solution small a. Now what you can do is take analytic prolongation on the counterclockwise sense, and there's another, okay, maybe now it's more visible, so you see, but now small a became big A. And so the subdominant became dominant. You go on again, and now it became small c. It's not done because there's a ramification, so you turn once more. Now the darker gray region amounts to the fact that it's covered 2 times, but also by small a and by big C. You do it again and again. And what you find is this picture, okay? So what I'm claiming is that, in fact, in this picture you can encode everything. And this is a picture that you can find in several places. For example, I saw it in a talk by Konsevich at Tohoku last summer, and then you can see it in works by, I forgot, I hope I don't forget anybody, but maybe Schende, Troyman, and Zaslow. Then there is another work by Schende, I forgot unfortunately the name of the Japanese collaborator, I wrote it, sorry, this is not good, Takeda. And okay, so let me convince you that you can encode everything here. So there are, let me make the link with the 2 previous descriptions. There are Stokes multipliers or else filter Stokes local system. So let me go on. This is the picture. Now, how you should think about it? You should think about it as a kind of way of encoding a constructible sheaf, which is locally constant along the stratification that you see, okay? And then the Stokes have a rank which is dictated by the picture that you don't see, but I explain. So it's white near infinity, which means Stokes is 0. Then it's light gray in these 3 regions, and there the Stokes should be C, dimension 1, and in the dark gray region the Stokes should be of dimension 2. Moreover, this constructible sheaf should satisfy the property that if you pick up any outgoing direction from infinity, there exists a small sector, small sectorial neighborhood, where your sheaf is really isomorphic to the direct sum of the constant sheaves on the outward going regions. Okay, so let me do it, for example, for the first Stokes direction. This guarantees that if you take a sector, in this sector you can trivialize your corresponds to the grading of the, okay. But then you can do it also on the next, and if you do it on both, there is an overlap, and in the overlap, your sheaf is trivialized, so what you get is an automorphism of the direct sum of the 2 constant sheaves on the subdominant and dominant components, and these are the Stokes multipliers. Okay, so you can find everything encoded here. Second way is through Stokes filtration. So in this case, you need to pick up an exponent, and what you need to do is also to consider the local system of solutions on the circle. So you should think of the big circle as the circle which is the circle of directions, not at 0 but at infinity in this case. So this is a local system. In this case it is constant because the functions are entire, but in general it's going to be a local system. Then you pick up an exponent. For example, in this case I chose phi equal to a constant times z square. You draw the same picture that Stokes did, and you see this curve, okay? Then this curve, what you should deduce, of course it is the same thing as the circle outside, because you can connect, it's drawn in polar coordinates, so 1 point here corresponds to 1 point there. And you can consider the R constructible sheaf on this blue curve with the same prescription. So it has Stokes 0 in the white region, Stokes dimension 1 in the light gray region, and Stokes of dimension 2. I mean, I don't pronounce correctly English. Stokes is not Stokes, but Stokes, the Stokes of a sheaf, okay? Sorry. So you see that it is actually, by prolongation, you can see it as embedded in L through the outward projection, and this is Stokes filtration, okay? So the idea is that in this picture you see everything, and now I want to show you how the construction of Kashiwara and I actually finds this kind of pictures automatically inside. It's going to be a kind of vanishing cycle at infinity of our sheaf.
The Stokes filtration is just the subdominant solution in these sectors. I don't see why it's so complicated.
No, that's the grading, but
It's the subdominant filtration.
if you use multi-summation, but I don't.
No. It's the usual Stokes filtration is given by taking the subdominant solution. That is the step in the filtration. It's just the solution on the sectors.
In this case, it's slightly more complicated because it's ramified. But anyway, maybe we can discuss about it later. Okay, but let me say that it fits with the picture that was explained to us these days. Okay, for example, Earthling just okay, but I'm willing to discuss. Anyway, forget best solution. Completely forget about that and just think of this picture. Okay, I like it more, and it's okay. So you just think about a constructible sheaf whose stratification, singular stratification, is the one that you see. And such that if you take any direction, you can find a small sectorial neighborhood where it is isomorphic to the direct sum of the subdominant and dominant contribution. Forget everything else, okay?
But that isomorphism is not given.
No. I mean, you choose it, but once you choose it, then you can write matrices. But if you don't choose it, you cannot write matrices. But I don't care to write matrices in general. Okay, so... now, I have to explain what's this enhancement. And in order to do it, you see that, of course, we need to have some framework where it's possible to keep track of growth of solutions, like tempered growth, that appeared in the discussion before. Okay, so it's important to keep track of tempered growth. It is not possible to do it shift theoretically in the usual sense, but there is a work from 2001 by Kashiwara and Schapira, a modification of sheaves adapted to this kind that I'm going to present you. And in order to do it, you don't really need to be in a complex framework. It's a purely real construction. So I will try to be systematic. X for me will always be a complex manifold, and M will be a real analytic manifold. So let M, when I finish erasing, let M be a real analytic manifold. And if you don't mind, I would like to recall what's a sheaf. M, real analytic manifold. I denote by mod Cx the category of sheaves. What's a sheaf? First of all, it is a pre-sheaf, and pre-sheaf means that you consider open subsets in M, and then there is a way of associating to each open subset a vector space. Its elements are called sections, and there is a way of restricting things. If you have a series of open subsets like this, it makes sense to restrict to V and get a section in V, and there is a compatibility condition. And then second, you can patch things together. If you have an open cover indexed by some set I, and if you have a collection of sections on the small open subsets satisfying a compatibility condition on double intersections, then you can find a global section that recovers those by restriction. Unique. Okay, this is a sheaf. Now, what's a sub-analytic sheaf? So sub-analytic sets are a very well-behaved family used by Hironaka in his desingularization theorem. They contain semi-analytic sets which are given by analytic inequalities, but there is more. They are also stable by proper push-forward. I don't want to enter into the discussion of precisely what they are, so let us believe that they are a very nice family, very nice in the sense, for example, that it is stable by intersections, by complement, by locally finite unions, really good family. So the idea by Kashiwara and Schapira is to change the definition. So what's going to be a sub-analytic sheaf is the same thing as here, but you add some requirement. You want that U not only to be an open subset, but relatively compact and sub-analytic. And you require that the gluing condition holds only on finite covers. That's it. Okay, so you could present it as usual sheaves in a suitable Grothendieck topology, but I think it's easier to digest in this way. And now, if you have usual sheaves and you have sub-analytic sheaves, there are natural ways of going from one side to the other. For example, of course, the requirement of being a sheaf is stronger than being a sub-analytic sheaf. So there is an embedding that I denote by iota, like this. It has a left adjoint alpha, which in turn has a left adjoint beta, which is again an embedding. So iota is clear, and alpha and beta are not difficult if you want to describe alpha. So let me call G a usual sheaf and F a sub-analytic sheaf. So for us, these are going to be the normal things, more or less, okay, depends. But so what's, for example, going to be alpha of F? It should be a usual sheaf, and what you can do, you can sheafify. So this is the sheaf associated with the pre-sheaf associating to U the limit of sections. Sorry. Let me change notations. You take, so in my notations here, so I'm sorry, I try to follow the alphabetical order, but I'm not even able to follow the alphabetical order. So F is associated to U and G is associated to V. And so this is any open subset. And this is a sub-analytic open subset. U is going to denote sub-analytic, F sub-analytic, V arbitrary, and G arbitrary. So that's absolutely natural. And beta, it's again the sub-analytic sheaf associated with, now you start from U, and you take the direct limit of V containing U, of G, of V, and actually containing, that's important, U bar. Okay? You can do it. And you can check that this is an embedding. Apart from these functors, there are other. Functoriality is important. So if you have a morphism of real analytic manifolds, then you can define the usual operations. So let me just list them with some remarks. I mentioned up there the proper direct image with two exclamation points. Every time that you write something different from the usual means that it is not compatible with the embedding. So if I take a shift G here and I take the proper direct image and then I plug it there, I don't get the same thing as plugging it there and then type it. Okay, so this is just to remind you that it's it's incompatible. But I will show you some examples. And so then there is a Verdier duality, then there is a pullback, there is a usual push forward, there's everything that you want. There is a tensor product, and there is an internal Ohm functor that, again, be careful a little bit, I denote with an I, it's not compatible with the usual one, but if you sheafify, so alpha is a way of getting a usual sheaf. If you take the usual sheaf associated to this new thing, you get the usual arom in the sense that turns out that these are subanalytic sheaves, like sheaves form a stack. So there is a stacky om, and you recover the stacky om as in this way, okay? But let me give some examples. The first example, which is of interest for us, is the sheaf of tempered distributions. And it's defined as follows. I will denote by dBm the sheaf of Schwarz distributions on M. And tempered distributions means that they can extend to the full space. From a given open subset, they extend to the full space. And they are called tempered because it amounts to a condition of the growth, on the growth at the boundary. So I mean, Kashiwara and Schapira define, inspired by previous work by Kashiwara on the Riemann-Hilbert correspondence in the regular case, you can define tempered distributions as the image of the morphism from Schwarz distributions with no conditions. So it means, as I said, that you consider only those distributions that you can extend in some way to the full space. Okay, so these are tempered distributions. A growth condition is encoded there. Now, if you sheafify in the usual sense, you lose all information. But if you consider it as a sub-analytic sheaf, then this pre-sheaf is already a sheaf. Okay? So this is a claim. It is a sub-analytic sheaf. So as I said, if you consider the usual sheaf, you lose all information and you recover the classical distributions without any condition of temperedness. But it's useful nevertheless, because if before taking the usual sheaf you do an operation, so for example, note that if you do RE-om, so this is the inner om for subanalytic sheaf, you take the constant sheaf on an open subset extended by 0, and you consider it by iota as a subanalytic sheaf. If you do this kind of construction, as I said, you get a subanalytic sheaf, but then you can consider the associated sheaf, so this is the same as ROM. And this is interesting because it's a usual sheaf, but encodes some growth conditions at the boundary of U, not all over, but at the boundary of U. Okay? That's the first example. Actually, it's a very important example because then if you go back to the complex setting, you can consider the sheaf of tempered holomorphic functions. Holomorphic functions are the Dolbeault complex of distributions. So you consider the Dolbeault complex of tempered distributions. In the usual setting, the Dolbeault complex has cohomology concentrated in degree 0. It is no longer true here in dimension higher than 1. I don't care, and nevertheless, it is an object in the derived category of subanalytic sheaves. Moreover, you see, tempered distributions, you cannot take a differential operator and act on it, because if you take a differential operator on U, you have no control on the growth at the boundary of the coefficients, and so you lose all information. But there is a functor, which is the beta up there, which is defined so that its sections are sections on a neighborhood of the closure. So in this case, you can have beta of the act on the BT. So to be precise, this is an object in the derived category of beta D modules. Okay? So that's an interesting gadget, very interesting, and one is tempted to compute, instead of computing usual solutions, you can compute tempered solutions of some D module, which means D-linear morphisms from M to OT. Of course, you have to put a beta here, and actually you have to write I om, okay? So that's an interesting gadget to try to study the modules which are possibly irregular. And let me see that, in fact, in this way, you do indeed keep track of some information that otherwise would be lost if you took usual solutions. So the second example is a computation of solutions of an exponential, which is irregular. So let me consider the case in which M is just R seated inside of C. I denote by Z the coordinate here and X the coordinate on the real line. And I consider the exponential 1 over Z, which corresponds to the operator Z squared D plus 1. It's irregular, and the associated cyclic module is just exponential of 1 over Z. I want to compute solutions of e to the 1 over z in this setting. Okay? To simplify, I don't compute holomorphic solutions, I compute distribution solutions. So I need to ask to myself, if I take a tempered distribution, which is a solution of P of u equal to 0, what kind of solutions do I get? And you can remark the following thing. If you have that P of u is equal to 0, then u should be of the form some constant time exponential of 1 over x. But of course, depends if you come from the positive side or the negative side to the origin, from the real line, the exponential can grow exponentially fast or decrease exponentially fast. Okay? So if you grow exponentially fast, you are not tempered, but if you decrease exponentially fast, you are. And so it turns out that this is tempered on some open subset if and only if you come from the right side. And it means that the origin does not belong to the intersection of u with the positive open half-line closure. Okay? So if you take this into account, you can now describe what are tempered distribution solutions. Tempered distribution solutions means that you want to understand the cohomology of this complex. And turns out that it has cohomology only in degree 0, so only the kernel gives a contribution. And you can describe it in the following way, thanks to that. So it's just the constant shift on x smaller or equal to 0. If you come from the left, everything is fine. But if you come from the right, you get a limit for epsilon going to 0 plus of the constant shift on x strictly greater than epsilon. And if you want to be precise, it's important. This is a usual shift. You need to consider it as a Sub Analytic Shift, and the same here. Okay, so this is the answer. And this guy here is an interesting, second interesting example of a Sub Analytic Shift, which is new. It's not really interesting in the usual sense. Why? Because if you shiftify, you lose all information in this sense. Let me call G, by definition, is sorry, let me optimize. Okay. Let me call G the same thing, but written in the usual sense. So I take the limit of the usual constant shifts on x greater than epsilon. So if this is a usual shift, you can compute it just the constant shift on the real half-line. But what we have here now is this other guy, which is the limit done in the subanalytic sense. And I claim that they are not isomorphic. Why is it so? So I claim that they are not isomorphic. Because, for example, if you consider U the open interval 0, 1, then if you compute sections of G, the usual sheaf on U, you get constants. Okay, 0, 1 is included in the positive affine. But if you compute sections of F, you get 0, because it belongs to the boundary. Okay, so it's a new guy. And since it is a new guy, like before, you need to be careful. If you yeah, real line, to simplify. You can do. I'm going to tell you what's the result in the complex setting, but okay. So in order to be careful, let us put some quotes around the limit when it's done in the sub-analytic sense, and no quotes if it's done in the usual sense. Okay. Now, sorry. This one? So one possible explanation is that if you believe to this computation, then in order to give something non-zero, you should have a tempered distribution solution of the homogeneous equation. And if you believe the explanation, you have none, because 0 belongs to the closure. Another possibility, another possible explanation is that, in fact, the quotes are there because you can interpret those as ind-sheaves, in the sense of the linear. And then what happens is that if you want to compute f of u, it turns out that this is exactly the same thing as the limit for epsilon that goes to 0 plus of sections of the usual sheaf C x greater than epsilon computed on u, because it's an ind object. So ind, the limit comes out of the ohm. And anyway, it gives 0. Okay, u here is the interval 0, 1. Sorry? Yeah, that's the constant sheaf on the open affine extended by 0 to the full. Yes. Okay, so now you have some information on the irregularity, because you see that the positive affines plays a different role with respect to the negative affine. But this kind of information is not enough to reconstruct your original D module, because you see that if instead of writing 1 over z, I write 2 over z, what I find here is a system which is cofinal to the previous one. So this kind of construction does not distinguish between e to the 1 over z and e to the 2 over z, and these two D modules are different. Okay, so we need to add some more, something more, and this something more is what okay, Kashiwara and I did. There are several problems. I try to do them one at a time, and the first problem is that we would like to. Okay, so maybe first I give you first result that we obtained. So this is very good, but not enough to reconstruct. And one of our claims is the following. So theorem: if you take a holonomic module, you can reconstruct it from something which is not far from this. So you take tempered solutions, not only of M, but you add one variable, and you take the exterior product with exponential of tau. So here I added one variable, and the idea is that you have R sitting inside of C, sitting inside of a real projective line, complex projective line. I denote by tau the affine variable in C, and I will denote by T the affine variable here. So that's a preliminary statement that we will obtain. Okay. So you see that if you believe to this statement, we need to deal with things like those. This is exponential tau. Here it was exponential 1 over z. So again, the role played by 0 here is infinity there. Okay? So if it's infinity there, you see that all the interesting information here sits at 0. And so there will sit at plus infinity. The trouble is that if you take these exponential, if you take the tempered solutions, for example here, let us say here, you take the tempered solutions and you restrict them to the positive half line. Then again, unfortunately, all the interesting information is lost. Because if you restrict it to the positive half line, for example, this counterexample, the interval 0, 1, you can no longer consider it as a relatively compact subanalytic subset. Okay? You need relatively compact. It is relatively compact in the full real line, but it is not in the positive half line. So the first problem that we want to address is how to be able to restrict to something without losing the information. And that's the notion of bordered spaces. Yes?
What's the symbol about the box times?
When I put a D, like up there, I just, mean the modulo operation. Yeah, because if you're used to a algebraic setting, you don't need to do anything, just take the usual shift theoretical external product. But I'm in an analytic setting, so I need to complete. Okay, to extend the scalars. Okay, so what are bordered spaces? They are simply a pair of a usual space and another one. So M is going to be an open subanalytic subset in M Czech, which is going to be a real analytic manifold, or if you want a subanalytic space more generally. So something modeled on a closed subanalytic subset. And so this forms a category in the sense that you can say what's the morphism between one bordered space and another. By definition, it's going to be a usual morphism between the open subsets involved, but with some control on the boundary. And the control is as follows. Denote by gamma f the graph of the function in the product. So, of course, it also sits in, if you put the Czech there, it's a locally closed subset here. If you take the closure of gamma f inside here, and you consider the first projection, you want that gamma f is proper with respect to P. So that's my definition of a morphism of bordered spaces. Now, if you use this category, usual spaces sit inside bordered ones if you don't put any border. So if you write twice M, you didn't put any border, and you can check that this is a fully faithful embedding of usual spaces into the... And there are some examples. For example, if you take M identity, M, and then the embedding into M Czech, this gives rise to an interesting sequence of morphisms. You start with M, you reach M infinity, and you go to M Czech. So you see that this guy sits in the middle between M and M Czech. Okay, so if you do this, then you can ask yourself what are subanalytic shifts on this kind of guys. And then you add one more piece here. So let us assume that M is a bordered subanalytic space. That I denote like this. There was a mistake here. It was an M. And now I put one infinity. So the only thing that you need to ask now is you consider open subset of X, which are relatively compact and subanalytic in the ambient space. Okay, so that's a small modification, but you solve the problem because now you see that 0, 1 is again relatively compact in this new sense because it's relatively compact in, sorry, I didn't say what's, yeah. Okay, so you can simply consider maybe I don't give the notations. Okay, so this solved the first problem, and now another thing that we want to do is that, inspired by some work by Tamarkin in 2008, we would like to really add one variable, like I said there, and in order to do that, I also need to define a convolution product, okay? Why? For example, one of the reasons is that if you take the product of two exponentials, the exponent that you get is the sum of the two exponents. So the tensor product at the level of the module should correspond to a kind of convolution so that, okay, that's one of the reasons. But let me define what's the convolution. And so now we can convolve because there is an interesting border space which is what we call R infinity. You can remember infinity in a sense. R infinity, for me, is the border space where R sits inside its closure, which is R plus the symbols plus or minus infinity. And as an exercise, you can see that as a border space, this is isomorphic to a projective compactification, whichever you prefer. And so now, what's the convolution? Okay, that's easy because in general, what do we do? You consider the sum. Maybe let me put some parameters. Let me call it mu. So x t1, t2 goes to x t1 plus t2. And of course, if I have two sub-analytic shifts on the product, m times r infinity, let me call them f1 and f2, I can define their convolution as usually. So you take the external product and you push it forward by mu. Okay, so if you do this, then this category turns out to be a closed monoidal category because the constant sheaf concentrated at t equals 0 plays the role of the identity. And it is again a well-behaved category in the sense that, for example, this functor has a right adjoint that we denote by R-iom plus, again. And you have the full set of operations. But we would like to do something more, and that's the last point of, then I give examples again. The something more is that now this additional variable plays too much of a role because it's interested for us only really at infinity. And so we are going to quotient out some sheaves. And so the final definition is that the category of enhanced sheaves is going to be the quotient of the one above by, there are several ways, okay, let me say, by those sheaves that give 0 when you convolve them with the constant shift on t greater or equal than 0. Okay, t was my variable here. And I should put a iota there, okay? So this is my definition. Usually, working with the quotient category is a mess, but Tamarkin showed in a similar case that, in fact, the quotient has adjoints, but maybe I'm going to skip it. And so just think that there is a quotient functor, but this quotient functor has a left and a right adjoint, which are full embedding. So full embeddings. So you can consider the category of enhanced sheaves as a full subcategory of the one before. And it is a very nice category in the sense that, again, you can use functors. And in this category, you have the functors that are written up there. What are they? So tensor plus, I explained. You need to check that it goes down to the quotient, but it does. And what's, for example, E double shriek? If you want to understand what EF double shriek is, by definition, it is simply the usual push forward, in the proper case, but of F times the identity of R. Okay, F times the identity of R induces a morphism from M times R infinity to N times R infinity. So you have a subanalytic shift here. You can push it forward in this sense. So that's a convenient notation because you don't see the additional variable here. And in fact, it doesn't really play a role because you can show that in a sense it's a stack on M. Okay. And now, last definition. There's a particularly good subcategory here, which is the category of what we call R-constructible sheaves, but enhanced. So what it means is the following. This is really related to usual sheaves, but with one variable more. And so the definition is the following. If you consider an object in this category, I forgot to put the sub here. If you consider an object here, it's called R-constructible. When you restrict it to any relatively compact open subset, subanalytic, now you can consider U infinity, which is U together with its boundary. And the requirement is that if you restrict F to U infinity, this is of the following form. So it's, I need to put another definition, but I don't know, well, let's say G. So there is a small things that needs to be done, but let me just so this guy here, by definition, is the limit when C goes to plus infinity of the constant sheaf on t greater or equal than c. And in a sense, it plays the role of tempered distribution solutions of e to the tau, okay? Our additional variable. So that's a very important component. What it does is essentially, since in the quotient, in this quotient, you see that before t equals 0 was the unit for the tensor product. Now t equals 0 is isomorphic to t greater or equal than 0. So the constant sheaf on t greater or equal than 0 is the identity functor if you take the tensor plus. So this functor here is just a translation from t to t plus c. And so when you do this kind of operation, you are moving your sheaf, your given sheaf, far and far away to infinity, in a sense, okay? But in a sub-analytic sense, so you keep track of information at infinity. And what you take is a usual, not sub-analytic, a real classical R-constructible sheaf, but up to the boundary. So it's a globally R-constructible sheaf, because you want to keep track of the boundary. Okay, so this is, but please, I mean, the important object, I understand that it's too much material, but this is really an object that is not, I mean, a classical sheaf. Okay, so now I'm done. I can state the theorem. Maybe first a lemma. And what happens is the following. So now let me go back to the complex setting. An example of irregular D-modules is given by exponential D-modules. So in general, if you take y, which is a hypersurface, and you consider a meromorphic function with poles on y, let me denote by dx e to the phi the cyclic D-module, I mean d over the ideal generated by differential operators that annihilate the function e to the phi where it makes sense. And then let me define by e to the phi to be the same thing as above, but you allow poles on y. So this is an irregular D-module in general. Anyway, it is holonomic. And so what happens is that one has the following proposition. Analog to the calculation that of course I erased, but was the computation of the solutions of e to the 1 over z. A generalization of that is the following. First of all, you need to define enhanced solutions. So it's essentially this thing here. So what are enhanced solutions? You can consider the following diagram. Consider x times r infinity, then you send it into x times the real projective line, and then you send it into x times the complex projective line. Here is tau, and here is t. Let me call I this embedding. So by definition, the enhanced solution of a D-module are obtained as follows. You take this guy here, and you send it in our new category. How do you do it? You simply pull it back. And then there is a shift by 1. It's a technical point, not important. But by definition, these are enhanced solutions. And then you can play a bit of a trick in the sense that you can also rewrite it in a nicer way as solutions, so D-linear morphisms with values in a new gadget that we call OX enhanced. But this is just a trick in the sense that here you need to solve both m and e to the tau. first you solve e to the tau, and that's the definition of OE, and then you solve M. So, okay, so OXE is just the solution of e to the tau, tempered solutions of e to the tau. And e to the tau is the solution of tau d tau. Okay? So, now this is the guy that I said solves the Riemann-Hilbert correspondence. Let me compute it in this case. So what turns out is that enhanced solutions of the exponential are just of the form that is, I hope, still written here. It's a guy of this kind. So, and the G takes into account, of course, the real part of phi that determines the growth. So what you find exactly is CE, X, tensor plus. So this is the important part, is the constant shift on T plus real part of phi greater or equal than 0. Okay? Let me call this here e to the phi with a different font. Okay, blackboard bold e to the phi. And the second point is that indeed, out of the enhanced solutions, you can reconstruct your original D-module because it turns out that e to the phi is nothing but R ohm. That's the stacky ohm that gives you back a sheaf, a usual sheaf, of that one into OE. Okay, so this is just a first taste of the kind of results. Now we are far from having proved the fact that we have, so this is in fact the factor that you need to use to go back. But if you want to prove the full theorem, now comes come into play the deep results by Mochizuki and Kedlaya on the description of flat meromorphic connections. And of course, I have no time, I'm exaggerating, but thanks to them, if you use their results as a black box, having proved this kind of result is more or less enough. Okay? So I don't give any idea of the proof. I had an idea, but I mean, I just want to show, can I show just the picture that are left? Because I promised that, okay. So why does the Stokes picture is inside here?
Since you are maybe here the OX to the E.
Yes. Yes, but I'm stuck to the. That's regular, not so interesting. Thank you. Okay. Anyway, as I said, this is the operator such that this is going to be MP if you call this P. I don't know what I was reading. Okay, sorry, thank you. If you derive the exponential, you get the same exponential, so it's d minus 1, I think. You're right. Okay, so last part. Maybe you will not see anything again because the colors. But okay. So this was the picture that I want to find, and this I just recall what was the Airy function. So if you do this procedure, you get e to the, I mean, what you get according to this picture is something which on a sector looks like exponential to phi plus minus. So when I said locally there, I need to be more precise. It's locally on a sector in the bordered space sense, but it's true. And so what you see, you find this kind of sheaves there. Okay? So this sits in X, which is an open subset in the complex plane, plus a real variable. And then what you need to do is to draw the graph of the real part of phi, maybe with a minus sign. So I should draw two surfaces, but then you don't understand anything anymore. And actually, what I want to understand is the behavior at z equal to infinity. So first, I only restrict myself to a small circle. I mean, C is very big, so that the circle is small around infinity. And so you can think of it as a kind of, as I said, vanishing cycle around infinity. Then you take the cylinder, because there's the additional variable, and I only draw the intersection of the graphs with the cylinder. Actually, not the graphs, but the upper graphs that's greater or equal than 0, and you get this picture, okay? So now you have the cylinder with the picture, you open it up like a flower, and you lay it down on the plane, and that's the picture, okay? I stop here.
So what's the main theorem? So you have a map from D modules to solutions?
Yes.
Okay. Modules to these enhanced sheaves. And the theorem is that that's fully faithful, or?
So maybe since it's a question, I can answer, right? Thank you. I didn't have time to state the real theorem. Okay, so this is what I stated. The situation is a little bit more complicated because the description here is not so clear. So let me switch to a triangulated setting, which is what I was into. This is the abelian setting. You can go from one to the other through T-structures, and actually we use the variation of the slicing by Tom Bridgeland to describe the T-structure needed here, but let us forget about it. I stay in a triangulated setting. So what we have is the following. You have the category of holonomic D-modulus, and then we have a way, which is enhanced solutions, of going into what I said is what I define, I mean, more or less I described, is the what are constructible enhanced sub-analytic shifts. And then I said that if you consider the functor R dot OE, you fall back into something. Actually, if this is much too big, because it is compatible with the usual regular correspondence for regular modules, where you were supposed to take the usual solutions, and then what you found here was C constructible. I mean, locally constant cohomology with respect to a complex analytic, not real analytic stratification. And so there is still something to be said here. There's a natural embedding that I didn't have time to explain. But this is what Kashiwara did in '84, written in terms of tempered solutions. So here you find a regular holonomic, okay. But here you have something which a priori is not even coherent, but there is a natural embedding of the first category into the last one. So what we claim is that everything commutes, and this is a fully faithful embedding, okay? So you could cheat and say C constructible, sub-analytic, sorry, sub-analytic has to be put here, by definition, could be the essential image. This is not a good definition. Not good, but it's a definition nevertheless. So if instead of this, you write this, then both become equivalences. But it's not the interest of the Riemann-Hilbert correspondence is that you have analysis, which is systems of PDEs, then you have topology, which is monodromy. And you would like to have a description here of this kind. But last year, Mochizuki proved a result in this direction. So he proved that if you want to check whether something is in the essential image or not, it's enough to test it on curves. Okay? So if you test it on curves, you are back to the Deligne-Malgrange case from the 70s, from the 80s, I don't know the date, sorry, from the 80s, 90s, late 80s, early 90s. So there you know everything, and the pictures that I was drawing, I mean, Stokes was drawing before me, are exactly to tell what happens in dimension 1. Okay, so there's still something missing. It would be nice to have a purely topological description of what you find. The trouble is that you have a kind of a mixed situation in which you have something which is real analytic, but coming from a complex analytic component. And